Okay, hello everybody. For those of you who don't know me, I'm Akhiad, and we will discuss sequence models today again in this tutorial. Our agenda for today will start with a recap of RNNs, and then we'll dive into some issues with training them in practice. And then we'll look at the RNNs enhanced with memories, and specifically we'll look at LSTMs and try to understand how they tackle these issues of training recurrent neural networks. And finally, we look at some use cases of transformers in other computer vision problems beside vision transformers that we saw for classification in the sequence lectures. And this tutorial will be built more like a lecture than an actual tutorial, but you're always welcome to ask questions and interrupt me. So to recap on RNNs, on the simple RNNs, remember that the RNN calculates a hidden state based on a function of the previous hidden state and the current input. And specifically when that function takes the form of the weight matrices multiplied by the previous hidden state and the current input, and then passed through a tonnage, we term this the simple RNNs or vanilla RNNs. Now, if we just think about
WHH?
This is the weight matrix for the hidden state, and this is the weight matrix for the input to the hidden. Okay? And we can also think about these weight matrices as concatenated, and then we also concatenate the H from the previous time step and the input, and then we can think about it as just one big weight matrix. Okay? Now, if we think about multi-layer RNN, just to understand this a bit deeper, we at the first layer, the rule is as we discussed, but at the upper layers, what we get from the bottom instead of the current input is the current time step, but previous layer hidden state. Okay, so that's how we pass it to a multi-layer RNN to eventually arrive at the output for each time step. And from the left, we will still be getting the hidden state from the previous time step. Now, we previously saw the attention weights to try to understand what attention weights are learning, but we can also try to find interpretation for what RNN cells, simple RNN cells are learning. And the authors in this work try to train RNNs with various sequence data, character data, and try to find cells that activate for specific inputs that we can understand what they are actually learning. So if we look at this sequence, we see red as being activated and blue as non-activated. And in this sequence, we can't really find anything sensible that can tell us what the cell has learned for this sequence. But we can find cells in different training regimes where we do have some interpretation. So in this sequence, we see that the RNN, the specific RNN cell, starts to activate inside a quotation and stops the activation when the quotation ends. And we can think about this as the quote detection cell. The authors also showed a different cell that gets activated as we go deeper and deeper in the sequence length. And this can be thought of as a line tracking cell. If we look at RNNs trained with code, we can. The authors also showed this cell which activates inside an if condition statement, and this cell can maybe help us understand when an if statement begin in the code, and can thus be helpful for next upstream predictions. And another interesting cell the authors showed is a cell that activates as the code gets deeper and deeper, and as we can see here. So this is a quick recap of what RNNs are and what they can actually learn. Now let's talk about the gradient flow in vanilla RNNs. So the rule is the same as we discussed, and here we have a graphical description of this RNN cell. And if we think about the gradient flow, when we think about going from the current hidden state to the previous hidden state, so we think about the derivative of ht with respect to ht minus 1, we see we pass through the span age and then through this multiplication by the weight matrix. So the derivative will have this form, and specifically note this matrix here, the multiplication by the WHH matrix, okay? Actually, the transpose. Now, if we take this one cell and expand it through time and look at the derivative or the gradient flow from the last cell to the first cell's weight matrix. So if we think about this derivative, what do we get? We get this series of multiplications by this derivative of the current hidden states in respect to the previous hidden state. So that's what we do in each cell here when we go back. Why is this a problem? Again, let's go back to this rule of this derivative, and we see we have this matrix here. Now, we can simplify all of this and think about the entire rule as being this a matrix W raised to the power of the sequence -1. And now we can maybe understand why this is problematic as T gets larger, as the sequence gets larger and larger. What's the problem here? Let's think about first if this was a scalar. If this was a scalar, and the scale was bigger than 1, we would raise it to a big T, we'd get a very big value going to infinity. And if the scalar was less than 1 and we raise it to big T, we would get 0. So in the matrix cases, if we have a largest singular value that is higher than 1, when we raise W to the power of T minus 1, we will get exploding gradients. And when we raise W to the power of T minus 1, when the largest singular value is smaller than 1, we will get vanishing gradients going through 0. And this prevents the vanilla RNNs from actually learning long-term dependencies, because the gradients don't support this as T gets larger. Now, what can we do about this? For exploding gradients, there is a simple heuristical solution. And it basically means just to scale the gradient if its norm is too big. This is called gradient clipping, and it's used in practice and it's easy to implement. But what about the vanishing gradient? For vanishing gradients, we have no such simple heuristic. And therefore, we can think about different solutions, but in this case, let's look at the solution that changes the vanilla RNN architecture. And this is our introduction of the LSTM. LSTM is one example of these memory-enhanced recurrent neural networks. There are other examples that we will not talk about them today, but they all have similar, somewhat similar rules for calculating the hidden state. Now, on the left, we see the vanilla RNN update rule for the hidden state. Notice that for the LSTM, we keep another vector called the cell state vector. And we can think about this cell state vector as the internal memory of the RNN cell. Now, just to look graphically at vanilla RNNs, so we will understand the next slide better, remember that we just take the current input and the previous hidden state, we multiply by a weight matrix and pass through a time H. That's the vanilla RNN. Now, when looking at the LSTM graphically and with the update rules, we see first, let's first look at the cell state or the memory. This comprises of a G gate multiplied element-wise by an I gate and an F gate multiplied element-wise by the previous cell state, the previous memory. What does this mean? Why would we use this update rule? So to understand this, let's first look at each one of the gates. So we have the input gate, the forget gate, the output gate, and the G gate. Let's start with the G gate. The G gate takes the previous hidden state and the current input, multiplies by a weight matrix, and passes through a time H. And this is exactly the same as we do for the vanilla RNN update. So we can think about this G gate as the vanilla gelato or Glida gate, okay? Since we don't have a good name for it. This will now be termed the Glida gate. And as we said, this is sort of similar to the vanilla RNN. Now we have the input gate. Notice that the input gate uses also the previous hidden state and the current input, but passed through a sigmoid. Tiny h gives us values between -1 and 1. The sigmoid will give us values between 0 and 1. So the I matrix, or the I gate, the input gate, will be a matrix of values between 0 and 1.
Yeah.
Yes.
Question. So this like vector of functions that you wrote here is just like a notation representing which function corresponds to which letter, to which gate, right? It's
Exactly. If you think about the big W matrix as being divided into the weight that is applied to the input gate, forget gate, output gate, and Glida gate, then exactly as you said, each function here will be applied to that part of the multiplication.
so it's different weights for different gates, right?
Exactly, exactly. You can think about it as 4 sets of weights for each one of these gates. And now going back, we already said that the input gates consist of a matrix of values between 0 and 1. And this is multiplied element-wise by the Glida gate. What does this mean? If we think about the cell state as being a memory, and the Glida or G gate as being the current input and the previous hidden state, this means that the I gate will tell us for each element how much do we want to write into our memory. And that's what we get in this part of the update. Now looking at the left-hand side of this update rule, we have the forget gate. Again, the forget gate is calculated using a sigmoid. Again, values between 0s and 1s. And this forget gate is multiplied element-wise by the previous cell state or memory. So we can think about this part as being how much do we want to forget for each element the memory we already have. So at each time step, to calculate the cell state, we are deciding how much of our current memory we want to keep and how much we want to write into our memory. And that's the reasoning behind calling this C, cell state, a memory. Now, what do we do with this CT? We pass it through a tanh and then multiply it element-wise by the output gate, again with a sigmoid, again values between 0s and 1s. So in this case, we will decide how much of our internal memory we want to output for each element. And this will define the hidden state for the LSTM cell. And so we have, after all these calculations, a new hidden state calculated and a new memory or cell state calculated.
Yeah.
Now, yes.
Question about like the values in CT. Do I understand correctly that CT has values only between -1 and 1, right?
If you think about this at each time step, at the beginning, you will only input into memory values between -1 and 1, right? Because we have -1 or 1, between -1 and 1 in G, and we're deciding between 0 and 1. But we do this at every time step. So eventually we can get larger values in CT. It doesn't have to be between -1 and 1. When it passes through this tanh, then it will be between -1 and 1, right? And again, we'll do this multiplication by the 0 and 1, and this is our normalization of CT to be between -1 and 1. Okay? Any other questions?
Just to ensure,
Yes.
I, F, and O, they have different weights, right?
Yes. I, F, O, and G, all of them have different weights. So we can think now on W as being divided into these 4 parts, and each part corresponds to this different gate. So there are different weight matrices for each gate. So coming from this question, we can also understand that this LSTM cell has much more parameters than the vanilla RNN cell, which only had the weight matrices for the W and the input. Okay. Any more questions on this?
Can you repeat what is the O represent?
Yes, O is called the output gate. And let's see where we use it. We use it when we calculate the hidden state, not when we update the memory. So the output gate represents how much of our current memory we want to use to calculate the hidden state. And remember, the hidden state is what will be passed forward to the next cell, but this hidden state is also what will be used if we want to predict something out of this cell, going to the output, or in a multi-layer LSTM going to the next layer. So this hidden state is what decides what's our output from the cell, and the O gate, the output gate, decides how much from this memory activation we actually want to output. Now, so just so you don't get me wrong, this is not the only way to calculate something like this memory. There are different update tools, and they are called other types of recurrent neural networks like GRUs, which are also common. But LSTM is the most common, and even after a lot of work from people trying to find better update rules, there isn't any other clear winner. So we can think about, even though this doesn't have to be the case in updating the hidden state, we could have imagined dropping this output gate. We can think about this as one way to solve this problem, or we have and have a memory and a hidden state inside the cell. But going back to why we came to LSTMs, we talked about the gradient problems of vanilla RNNs, right? We discussed the vanishing gradient problem. Remember that the vanishing gradient problem came from this raising a matrix to the power of the sequence length, -1. Can anyone see why maybe this will be better in terms of this vanishing gradient? What do we gain from this architecture? Feel free to comment anything, and if not, I will try to explain this. Let's think about the derivatives here. If we think about the derivative of the hidden state or the derivative of the cell state, do we see what we gain here in terms of matrix multiplication? Well, I'll give you a clue. When we go through the cell state, going backwards in calculating the gradient, what operation do we have here? We have an addition operation, right? This only routes the gradients. And then what do we have here? We don't have a matrix multiplication. We have an element-wise multiplication by the F gate, which is just a matrix, right? But crucially, this weight matrix is different for every cell in the sequence. It's not the same F matrix in H2 or in LSTM cell 2 or in LSTM cell 3. It's a different weight matrix. So what we gain by this architecture, if we just look at the cell state or the memory, we get that our gradient will not depend on a matrix exponentiation, a matrix raised to a power, but it will be an element-wise multiplication and by a different matrix at each time step. And this will allow us to have some gradient highway, to have the gradients flow backwards in time without interruption or vanishing towards zero because of a matrix exponentiation.
Akhiad?
And yes.
Why are the weights different from each hidden state? I mean, wasn't it the point in the RNN that it's the same weights?
The weights for the forget gate are the same, but the forget gate itself is not the same, okay? So while we only maintain one set of weights for the forget gate, when we go backwards in time through the LSTM cells, think about going, as we previously discussed, from the last state to the first state. If we have this highway here, at each time step, we're going through an F matrix that is not the same. And only when we actually want to update the weights, we will go through the weights. Okay? And this is what makes this architecture have a highway for gradients flowing from the beginning to the weight matrix we want to update at each time step. And does this ring a bell, sound similar to anything we already learned in the course? Maybe this addition can be viewed.
Skip connections.
Exactly. This is not, of course, exactly like skip connections, but we can think about it as serving the same function. Having this skip connection allowed us to have this highway for gradients. And the same here, this LSTM rules allow us to have gradients that flow much easier from the later time points to the first time points. Okay? Now, again, if we think about multi-layer LSTMs, as we discussed, we have this cell memory, cell state that is flowing through time, but only the hidden state will be passed upwards to the upper layers, and also only the hidden state will be used to calculate any output we want to calculate. Okay, so that's why we can think about the cell state as the memory and the hidden state as the output. Now, in PyTorch, implementing an LSTM is, as we can imagine, fairly easy. Yes.
So LSTM, the purpose of LSTM was to solve the problem of vanishing gradients or exploding gradients, or is it like a nice outcome of the architecture?
Well, first of all, LSTMs were already conjectured in the 1990s, so I'm not sure exactly about the process, but when I look at the first LSTM paper, it addresses the vanishing gradient problem of RNNs. So it might have also been thought of based on this concept of memory, which is maybe beneficial in other manners except for the vanishing gradient, but the authors were aware of the vanishing gradients of RNNs. So at least it has some part in it. Okay?
Thanks.
So the LSTM is in PyTorch is very easy to implement. What we see here is that we have the embedding dimension or the input dimension that we want to embed, the hidden dimension, and the number of layers. And that's all it takes to get an LSTM in PyTorch. And now we said LSTMs, we introduced LSTMs as a solution to this vanishing gradient problem. Does it actually solve it? Well, first, in terms of practical use case, it does solve it. Let's think about it as yes. Why? If we try to train vanilla RNNs on simple problems, and you will see this in the tutorial number 4 assignment. If you try to tackle it with vanilla RNNs, you get a lot of problems in training, a lot of playing with hyperparameters, and sometimes it still doesn't generalize to large sequences. And LSTMs are surprisingly simple to train, even for long sequences. So if we think about the problem as being solved by practical use case, then yes, LSTMs solve the problem. But actually, we can understand that all I said was a simplification, and LSTMs don't really solve the problem of vanishing gradients. And when we will go to higher and higher sequence lengths, we will still encounter this problem. But it does alleviate this problem. It allows the model to learn longer term dependencies than the vanilla RNNs. Now, again, in the sequence lectures, Shai introduced all these ways of processing sequences. And we talked about recurrent neural networks, so also 1D convolutions. And then we discussed self-attention. And self-attention was used in the transformer layers. And from there, we got to the vision transformers, the transformers that are actually used without any RNNs. And then they are able to solve problems in computer vision to state-of-the-art level results. If we think about, just as a reminder for self-attention, what we had here is a set of queries, keys, and values. The queries and keys were dot product and passed through a softmax to gain a vector of similarities between queries and each key. And then they were multiplied by the values, which gave us a representation for each input as a weighted sum of the values. That's the basis of self-attention. And self-attention by itself is the basis for this transformer layers, which have just multi-head, a lot of attention heads and a lot of layers and all the encoder, decoder part that Shai described. Okay? Transformers in PyTorch are also fairly easy to implement. And what we see here is just the dimensionality of the model, or the embedding. We can specify the number of heads for the transformer and the number of encoder and decoder layers, the dimensionality of the feed-forward network that is used to calculate the output, and the activation. And as you can see, this in PyTorch, everything is easy. Now, we previously in the lecture saw the vision transformers that were used for classification in images. But actually, even though these are the most recent, they are not the first use case of transformers in computer vision. And now I'll try to show you two other examples of transformers being used in vision. The first one is from a paper called End-to-End Object Detection with Transformers. In this case, as you can understand, the objective was to do object detection. And the authors built their architecture based on the notion of first passing images through a backbone of CNN to gain some feature representation of the inputs. Then passing it through an encoder, transformer layer, passed through a transformer decoder layer, and the output from the transformer decoders was viewed as a prediction for a bounding box, which was given after passing through a feed-forward neural network. And then for each bounding box, all the network had to do was decide if there was an object or no object in the bounding box. And if there is an object, then give the class of the object. So we previously saw object detection architectures that were very similar to this, but instead of an encoder and a decoder from a transformer layer, there were other mechanisms working here to generate the bounding box. And we can see that this is a fairly simple addition of transformer layers to tackle a problem and gain very close to state-of-the-art results, just based on this nice concept of transformers. Any questions on this?
How do they determine the number of outputs in the prediction head?
Okay, that's a good question. Maybe let's first ask, why are you asking this question? What is the meaning of the number of outputs? It will limit us to the actual number of bounding box we can predict, right? We can predict more than the bounding box and the outputs of this transformer if we think of this architecture. So the way they decide this is based on the maximum amount of bounding boxes they want to predict for each image. And this is, of course, a limitation of this architecture, because let's say we have a large number of objects in an image, this architecture will be limited in its ability to generate this amount of bounding boxes.
It's supposed to work on all scales, or you apply it to like a pyramid of the image or something?
So just as a brief reminder, also remember that we have a positional encoding here, if this answers your question. And if your question was about the size of the bounding boxes, then we can get different sizes of bounding box based on the feed-forward neural networks, okay? So if we think about this as being a representation of where objects will lie in the image, then this feed-forward neural network will just decide what's the actual locations of this of the bounding box surrounding the image.
No, I mean more of the training. In the training process, they just like give images with bounding boxes with different sizes and hope like it will be optimized altogether. Or
okay, okay. I think I understand your question. So it depends on how big the images are, right? Because what's the limiting factor of this transformers? We said it's this attention matrix, right? The queries dot producted by the keys will give us a weight matrix that is the square of the length of the input. Okay, so if we have too big of a piece of an image, we will be limited by the computational power or the memory. So in this case, for the images that they show here, the CNN took care of making the feature map small enough, and all of it was inputted into the transformer. Okay,
but the training, the data set's
yes.
supposed to contain, like in the test set, relatively similar sizes of objects, right? Because either, if not, then like end-to-end won't, like it won't work, right?
You are correct that in order to train this to have state-of-the-art results in multiple resolutions or multiple images, not images, object sizes, then you will either need to have multiple object sizes in the training or to have some handling of this in the training process.
And just one last question.
Yes.
Sorry. They deal with the non-maximal suppression as well, or it's like it's a post-processing part, or it's also optimized together in the.
So it's optimized together. They didn't use, as far as I can remember, they didn't use this, but we can look at it later, and I will send you the answer.
Thank you.
Yeah, and what are object queries here? What are those that are passed to the decoder?
Okay, what are object queries? So think about these object queries as if we want, this is not the actual way it was used, but think about it as if we would want to locate a specific object in an image. Or how would we do that? We would encode it with some embedding, and that will represent our query. And we will look for similarities in the encoder keys, and then we will find the values that we want to take in order to find the object queries, in order to approximate the object queries, right? So in this case, the object queries are learned throughout the training process. So they are called object queries, but think about them just as placeholders for places we want to predict a bounding box, okay? Some embedding.
So they represent the place, the spatial location in the image?
Not a spatial location, but a placeholder for one bounding box. If I didn't understand your question enough, we can also talk about it offline. Okay. Any more questions on this? I want to get to the last use case of transformers, but I will be happy to take any more questions if you want before I proceed.
Is the backbone pre-trained on a detection task, or it's just training for scratch?
The backbone is usually pre-trained on either image classification or something like that. Of course, this backbone is replaceable. You can use it with different backbones depending on what you want to do. And I don't remember the exact backbone they used in this paper, but usually it is trained on the classification, because what you want to get from the backbone is just an architecture that gets you good features from images. not and not like to have the best detection, object detection from this backbone. But again, you are right that we don't want this to this backbone to make the image too small, because then it will be hard to do this.
That was the question, and also the size of the patches for the input of the transformer encoder.
The size of what? That's the question again.
The input of the patches that are for the transformer encoder.
Yes.
So, what sizes are they? Because it also a limit for the size of the objects and the like the.
So we're asking like the dimensionality of the feature, how many features we get here?
No, the spatial dimensionality of the input to the transformer encoder.
Yes. So as we probably said, this this will limit either. This will be limited either by memory. So if it's too large, it will be limited by memory, and if it's too small, then we will have problems. The attention or the transformer layers will only be able to look at parts of the image. It will not be the receptive field will not be maybe large enough for big images, right? I don't remember the exact number of features they use here, but for small enough images, they just use the full image. Okay, the full, let's say, image representation of the full image.
So when you say full, you mean so the input to the encoder are pixels, not patches, not crops?
It's never pixels. It's a representation of pixels after passing through
in the feature map.
Yes.
Okay, thank you.
Of course, if we do it for pixels, it will be hard, right? Okay, so now looking at the image transformers. Here, the use case of transformers in vision was to generate images or to have a super resolution of low resolution images. And this was already revealed at 2018, 2 years or 3 years before vision transformers, okay? And why would the authors go into this domain using transformers? So there are various explanations, but one intuition that we can think about is that image generation can be thought of as a sequential process. If we think about each pixel being generated, conditioned on all the other generated pixels. So we generate a pixel, and then we generate the next pixel based on the previously generated pixels, and so on and so forth. So we can think about it maybe as a sequence. Now, we remember that transformers don't really keep this ordering of pixels generated, but at least that's the intuition. And the problems or in image generation or super resolution is either taking a low resolution image and encoding it in some manner and being able to produce a high resolution image of the same objects from the low resolution image, or having some latent decision of what image we want to generate based on maybe a class injected in the image. And in this case, in the left, you also see image completion, where we have an input of part of the image. We can encode that, and then we can try to predict the rest of the image to do image completion. And how? Let's look at the author's solution to this based on transformers. And I'm not going too deep into the generation part, since we already discussed this in the lecture, but I want to show the use of the transformers for the generation, okay? But if you have any other questions, feel free. So how are transformers used here? Let's first look at the architecture. We have here Q, which represents the current pixel we want to predict. So the embedding of the current pixels based on some features can be thought of as the queries here in the image transformers. the other surrounding pixels, or the embedding of the other surrounding pixels, can be thought of as the keys for the transformer. And just to look at how this is actually implemented, we don't use it throughout the whole image because this will be too costly. What the authors do is generate some memory block, either sequentially or by the 2D position. And this memory block will decide which pixels go into the keys, the neighboring pixels. Okay, that's the blue outline. And for this blue outline, the set of predicted pixels will be the ones in this black squares, okay? So and then we will move this outline or this square on the images to get a generation of different pixels, okay? So if we think of just one block, we have the set of queries will come from here, and the set of keys will come from all these pixels. Okay, is this clear? Good. No questions, so I assume it's clear. So now we have this embedding of current pixels, embedding of the neighboring pixels, and we again do this dot product and softmax to gain the similarities. And then the values are also the embeddings for the neighboring pixels. So what do we gain here if we think about it? And let's ignore all the rest, which is just drop out the normalization and a feed forward. What we gain from this values of neighboring pixels with the similarity between a current pixel and the neighboring pixel is just a weighted sum of the embeddings of the neighboring pixels, right? So the image generation in this context just means taking a weighted sum of already generated neighboring pixels. And if we think about now going back to our problem, to have this solution of a super resolution image from a low resolution image, what we can do is pass the inputs through an encoder transformer, and then use the decoder with the method as specified to generate a larger image, which contains features we wanted from the encoder. That's how we can do super resolution. If we want to sample just a new class, then we can just sample parameters for the latent space of the encoder from the transformer, and again do this process of generating pixels based on neighboring embeddings and the weighted sum of similarities. And if we want to do image completion, then the input to the encoder would be the part of the image that exists, and from the decoder we'll try to predict the missing part. And that sums up all of our sequence lectures and tutorials. In the last lecture we talked about the move to sequence model, recurrent neural networks, and attention and transformers. I remind you that LSTMs were missing, and that's the part that we had today, and we will also see it in the assignment. And we also saw other applications of transformers in vision. Please feel free to ask any more questions before we conclude. Maybe here. Okay, then thanks a lot, and feel free to also ask questions when we tackle the assignments.